In this video, I'm going to focus on how the unit circle can create graphs of sine, cosine, and tangent on the xy coordinate plane. Using review concepts from geometry, the special right triangles, and review concepts from Algebra 2, the xy coordinate plane, we will see how the unit circle actually can produce graphs. So the assumption in this video is that you have seen the video or understand how the first quadrant is constructed using special right triangles from geometry, and that you have seen the video or understand how those values extrapolate all the way around the unit circle to produce all of the values. All right, let's get started with the graph of sine. So to understand what's going on, the unit circle's purpose is actually a calculating device for angles and measurements for sine and cosine. And so in this particular case, since we're doing sine, we're going to eliminate the cosine values just temporarily so we can focus on sine. And so what ends up happening is I have a unit circle that's limited to inputs of angles and outputs of measurements. So I input 0, I output 0. That is my first coordinate pair. I input pi over 6, I output 1/2, making a coordinate pair. I input pi over 4, I output root 2 over 2, making a coordinate pair. I input pi over 3, I output root 3 over 2, making a coordinate pair. And pi over 2 and output sine of 1, making a coordinate pair. Now, looking at those coordinate pairs, you might say, how in the world are we going to graph these irrational numbers? The graph paper itself is set up with 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6 pi, and so on in the actual graph paper as a line to graph. And the output values, which many of them are also irrational, I simply type them in the calculator to get a value. 1/2 is 0.5, root 2 over 2 is 0.707, and root 3 over 2 is 0.866. So when we graph these points, we're just simply going to graph them on the graph paper. So also notice that when we do this, that the values keep repeating. So let's just take a look at the first quadrant. So 0, 0, and so on. 0, 0 is right here. This is pi over 6, this is pi over 4, this is pi over 3, this is pi over 2, this is 2 pi over 3, and so on. So at pi over 6, I've graphed 0.5, just like you see here. At pi over 4, I've graphed root 2 over 2, but I graphed it as 0.707. And then at pi over 3, I have graphed it as root 3 over 2, but here it's graphed as 0.866. And then at pi over 2, I graphed 1. So this right here are these points graphed on the unit circle. And then we start to repeat, but we need to remember that mnemonic device that we had. All students take calculus, because this really will help us with understanding how the graph works. All trigonometric values are positive in quadrant 1. Only sine is positive in quadrant 2, only tangent and only cosine in quadrant 3 and 4, which means these quadrants will have negative sine values, as you can see here. So at this point, we still have positive values. They're going to start high and go low. As you can see here, we start at root 3 over 2, root 2 over 2, 1/2, and then we're back at 0. That correlates right there. Input pi, output 0. And then we start having negative values, negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1. And this is quadrant 3. And in quadrant 4, we have the same values, but they start to go back to 0, and we finish our curve here, and this is what's known as a sinusoidal curve. And it appears that the domain of this graph is 0 to 2 pi. And the actual word for that in trigonometry is the period or cycle. And the reason is the graph will keep going this way and keep going this way, representing our coterminal angles and our negative rotations. As you saw from video 3, these values just keep going, and they also go in the other direction and are simply labeled different things. So this is 11 pi over 6, but I could also call this negative pi over 6, and that would be at negative 1/2, and that would be the dot that would be right there. So that original thing we saw is called the period, and that period is 2 pi. The domain is actually negative infinity to infinity in interval notation. Notice parentheses as a review, because I cannot include the value of infinity, so I have to use parentheses. And verbally, that is all real numbers. The range is negative 1 to 1, because the range would be negative 1 to 1. And that value right there, keep in mind these do curve back down, so that is the minimum and maximum from Algebra 2. They are inclusive, so notice I used a bracket. And so in interval notation, that would be inclusive bracket -1 to 1 inclusive bracket. Now that brings up another vocabulary word that's based on review concepts from Algebra 2, which is if the range is -1 to 1, in trigonometry, we have something called the amplitude, and that is how far a graph will rise or fall from its midline, always being a positive number because amplitude is how far distance is positive. Now this midline can move up and down using translations and transformations, which we'll talk about in a later video, but the definition of the amplitude is how far it goes from the midline to its min or its max, a connection to Algebra 2. Talk about the fact that this is a lot of information, and if the video is going to focus on parent functions, if you remember from Algebra 2, we only have usually 5 points for parent functions. So we like to focus on values that are the most readily understood. So typically we focus on these dots that I have colored in black because 0, 0, 1, 0, -1, and 0 are really easy to remember. And that makes 5 points. 0, 0, pi over 2, 1, pi 0, 0, -1, and 0, 0. So to graph the function, the parent function would only be this much as long as you know the curve, because you might accidentally draw some thing like that, which is not a curve shape. So the key points are 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0, drawing a sinusoidal curve, understanding that it does keep going infinitely in both directions. So cosine, similar process, but we're going to temporarily eliminate the sine value to use a calculation for cosine. And what ends up happening is we have the same idea. We're going to input 0, but now we're outputting 1, making this coordinate pair. Input pi over 6, output √3 over 2, input pi over 4, output √2 over 2, input pi over 3, output 1/2, input pi over 2, and now we're outputting 0. Now you might notice that a lot of these values are repeating. In fact, this value is the same for both sine and cosine. These values here are similar. These values here are just reversed. So we still have the same decimal equivalents, but what ends up happening is that this, instead of starting at 0, it starts at 1 and then goes downward. So you can see that we start at 1, then we have √3 over 2, then we have √2 over 2, then we have 1/2, then we have 0. So the graph starts high and goes down. And going back to that mnemonic device, all students take calculus. Notice what happens with cosine. Everything is positive here, but then only sine is, making cosine negative. Only tangent is, keeping cosine negative. And then here, cosine returns to being positive. So if you take a look at the next quadrant, we're going to be negative, more negative, more negative, to the minimum of -1. Then we're going to start going back to the x-axis until we get to 0, and then we're going to start going up again. So quadrant 2, you can see, is right here. Here is quadrant 3, we're going back up to 0, and then quadrant 4 going back up to 1. And again, it appears that the domain of this graph is 0 to 2 pi. That is, again, called the cycle or period in trigonometry. The actual domain, because of coterminals and negative rotations, right, going infinitely, is again -infinity to infinity. The range is inclusive bracket -1 to 1. I still have the same minimum and maximum Algebra 2 concept, and that minimum maximum yields this vocabulary word of amplitude, which is how far something rises or falls from the midline. Rises 1, falls 1. It is the range, but it has a different connotation in trigonometry. So the parent function points for this, again, there would only be 5 values. We're again going to focus on the axes values. So the parent function points for this are 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi 1. So tangent is created by dividing sine over cosine. Keep in mind this point is just a regular old point on the coordinate plane, and that point is 1, 0. Okay? So if I try to figure out what tangent is sine over cosine. So sine over cosine, or y over x, is 0 over 1, which is 0. But to create the pair, to create the coordinate pair for tangent, I'm not going to look at this. I'm going to look at inputting the angle of 0 and outputting the value for tangent of 0. So the first point for tangent is 0, 0. For the next one, I would input pi over 6, and I would output root 3 over 3, and that comes from dividing the sine and cosine values. I would input pi over 4, I'd input 1. In this case, the sine and cosine values are both the same, so it makes sense that that is 1. I'd input pi over 3, I would output root 3, which is, this is the sine, this is the cosine value. I would input pi over 2. Remember, this point is 0, 1, so it would become 1, 0, but again, I don't want to look at that. I want to look at inputting pi over 2 and outputting undefined. So a couple of things here. If you don't know how I got these values, they are included in my first video on the unit circle. They are simply calculations from, they're really calculations from geometry and rational equations from Algebra 2. These values I've typed into the calculator here because we have some new irrational values. And undefined, remember from the rationals chapter of Algebra 2, is an asymptote. So we focus here again on 0, asymptote, 0. We have another asymptote here and then back to 0. And these values we're simply going to graph as pi over 6 and 0.577, pi over 4 and 1, and pi over 3, and then in this case 1.73, and then an asymptote. So you can see those points right here. I start at 0. I then have a value at pi over 6 of 0.577, and then at pi over 4 I'm at 1, and then at pi over 3 I'm at root 3, which is 1.77, and then an asymptote at pi over 2. And then again, that mnemonic device, it's so important. All students take calculus, so all values are positive here, including tangent, but only sine. So notice tangent is negative. And then tangent is positive, notice the values are positive, and then cosine is positive, so tangents are negative. Please keep in mind also that tangent is understood as the slope of the hypotenuse of those special right triangles. So these special right triangles have a positive hypotenuse or positive slope value. These have a negative hypotenuse or negative slope value. And notice that these values, they correlate because they're the same line, right? They're the same line. So this is negative. These are both negative. These are both negative. These are both positive, 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 0, undefined. They are the same line and therefore have the same tangent or slope value. So going back to this, we're at the asymptote. Then we're going to have negative values below the x-axis. Then we're going to go back to 0 and have positive values. And then we're going to have an asymptote at 3 pi over 2. And then we're going to go negative again. And you can see that right here. Negative values at pi we're at 0, then we go back up, then we have an asymptote at 3 pi over 2, and then we have values here that are negative and then go back up to 0 at 2 pi. And the parent function values for that, I like to think of it as 0, 0, asymptote, 0, asymptote, 0, and then we do need at least one value to show the curve. And so we use the pi over 4 values, all of them 1, negative 1, 1, negative 1. So when I graph this, I graph it like this: 0, asymptote, 0, asymptote, 0, 1, negative 1, 1, negative 1, and then I show the curve that does sort of resemble a x to the third power or cube graph. So now let's talk about the interesting domains and ranges for tangent. The range, fairly simple, negative infinity to infinity. It looks kind of weird. It does have these asymptotes, but that does not affect the range. But when you talk about the domain, first thing I want you to notice is that the graph does keep going. So it does go this way, and it does go this way due to the coterminal and negative rotational angles from the unit circle. But notice that if you look at the unit circle, tangent completes all of its values: 0, positive, 0, undefined, negative, 0. It does it in pi, not in 2 pi. So you can clearly see that between these two asymptotes here, from pi over 2 to 3 pi over 2, you have 1 pi, and that represents, again, that actually represents from here, right? It starts here, represents from here to here. That's half the unit circle. So its period is pi, not 2 pi, okay? And that repeats. Again, it would also repeat here, and then it would keep going. And so it does have a domain that keeps going, but it's interrupted by these asymptotes. And you might have already looked like, whoa, what is that super long domain? It's actually a review of multiple concepts going all the way back to Algebra 1. So let's talk about it step by step. The first thing is x such that x is a real number. So we know that all the domain x values are real numbers, okay? But then we have these exceptions at pi over 2 and 3 pi over 2. And if this was Algebra 2 class and we were talking about asymptotes when we saw them in either in logarithms and exponentials or in the rational functions chapter, we would simply say the domain is all real numbers except x cannot equal 1 or 3. And so you can start to see that here. So where in the world did this come from? This actually is a review from the chapter on sequences and series. So I have a little demonstration of how this happens. So as you see, we have on this graph, we have asymptotes at 1, 3, there'd be another one at 5, and there'd also be ones at -1, -3, and -5. So if I take a look at that, I have 1, 3, 5, 7, and so on. So if I look at that, if I take that sequence of 1, 3, 5, and 7, and I apply the equation for arithmetic sequences, plugging in 1 and the common difference being 2, and I distribute and simplify, I end up getting the value, the equation -1 plus 2n. And that is the equation you see that I have put in here. It's actually reversed in this just because that's the way that trigonometry writes it. So for sequences of series, this would again be -1 plus 2n, but here we have 2n minus 1, and then pi over 2. So as you can see, this is saying odd pi over 2 values. This is mathematically saying odd from sequences and series, and then we have pi over 2. And the last problem is, well, what is n? N means number. So then we say, well, n is actually an integer, meaning n is actually 1 or 2 or 3 or 5 or 7 or 0. If I put any of those in there, I would have an asymptote. If I put 0 in there, I'd have negative pi over 2. If I put 3 in there, I would have 6 minus 1 or 5 pi over 2, the one that's over here. You can actually simplify this a little bit by simply putting z there, and this is traditionally what you see is someone will just combine those two and say x, such that x is a real number, but x is not equal to odd integer values of pi over 2. And I know that looks complicated, but if you would rather just write it out and say all real numbers except odd pi over 2 values, that would be a great start, and then you can try to piece this together one piece at a time. All right, I hope you have enjoyed this video, and I hope it has helped you with understanding how to graph graphs and use the unit circle to make parent functions for sine, cosine, and tangent. In this video, I'm going to talk about the transformation of trigonometric graphs. And we're going to do this by focusing on some Algebra 2 concepts that you probably learned when you did transformations and translations and compressions and stretches of Algebra 2 parent functions. So we have an A, a B, a C, and a D, which control these items. And please keep in mind that the B always has to be factored out before you can actually determine what C is. Now in Algebra 2, this might have been an H or a K, but in trigonometry, pre-calculus, calculus, upper level math, college, they typically just do A, B, C, and D for just alphabetical order. That H and K thing is not fairly used commonly all around in different areas. So the A, formerly known as a vertical compression or stretch, in the world of sine and cosine is called an amplitude. It is the distance a sinusoidal graph travels from its origin or midline to its min or max. Keep in mind here it says sinusoidal. So when we talk about tangent, it is again simply a vertical compression or stretch. The period, which is formerly known as the horizontal compression or stretch, it actually changes how it works, okay, depending on sine or cosine. Notice the definition. The interval that a function takes to complete one full cycle from min to min, max to max, or asymptote to asymptote if you're talking about tangent. So if you remember the unit circle, sine and cosine will repeat their value every 2 pi once around the circle. Tangent, however, will repeat itself halfway. So the period is 2 pi divided by b for sine or cosine, or pi divided by b for tangent. Okay, the phase shift is formally known in Algebra 2 as the horizontal shift. It is c. It is the amount the function is translated left or right once b has been factored out. Earlier mentioned here, you got to factor that b out. It is always a GCF, so it's an easy kind of factoring. The vertical shift, which is D, that would have been called K in Algebra 2 for some people, and that's just the amount the function is shifted up or down. Keep in mind, there's nothing weird going on with D. What you see is what you get. C, however, formerly known as H, that's negative. So it's actually opposite of what you see, which we'll look at some in the examples. A couple of interesting notes, which we'll see when we get through some of the examples. If you phase shift a trigonometric function equal to its period, the graph appears to not change, okay? And if you phase shift a trigonometric function 1/2 of its period, it will appear to create a reflection, meaning the max will shift into a min, and the min will shift into a max. Now, an example of this is the full moon. If you look at a full moon, 28 days later, if you phase shift forward equal to its period 28 days later, you'll see a full moon, right? And halfway through that, you would see half of that. So just keep that in mind, that this happens around us anytime we talk about cycles. So here is our first example of sine. And keep in mind that sine's parent function consists of 5 points. The points are 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. I simply just say to myself, 0, max, 0, min, 0. And you can see those right here on my graph. And so what happens next is I take these 5 parent functions and I draw them onto the graph, and I'm going to shift the graph forward pi over 2. That's not a mistake. Remember, C is opposite of what you see, just like H was in Algebra 2. So if this is negative, it's actually going to move the graph forward. And D, which used to be K, moves it up. So all I do is just one at a time. I take this point, I go forward pi over 2, up 1, forward pi over 2, up 1, forward pi over 2, up 1, forward pi over 2, up 1. And that will give me the graph that I'm actually going to graph as my sine graph. And it'll still look like sine, it's just going to be translated, right? So that's all you have to remember, is that the graph is still the same graph you're used to seeing. If you look at the graph that I drew right there, that is the same graph as here. It's just been moved forward and up. Keep in mind this graph does keep going, so the domain is -infinity to infinity. The range, however, would be, it does go through there, so 0 to 2. Okay, inclusive, because it does touch those values. So let's talk about some of that new vocabulary. You can see clearly right here from the midline to a max or min, we go 1. There's my amplitude. My phase shift is forward pi over 2. Okay, I do not have a compression or a stretch of any kind, but I do still have a period. And the period is, again, how long it takes to do this initial cycle, which is 2 pi, even though I've shifted it. And the easy way to determine that is the little algorithm that I mentioned right here, 2 pi divided by b, which in this example would be 2 pi divided by 1. So again, amplitude's 1, period is 2 pi, phase shift is right pi over 2, vertical shift was up 1. All right, let's take a look at a cosine example. Please keep in mind that the cosine graph has different values for its parent function, but there are still 5 of them. And the values are 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, 2 pi, 1. So again, I just think of it as max, 0, min, 0, max. Kind of looks like a V. Okay, so you can see that right here. It makes a curvy, mountainous, valley-looking graph and not a V. All right, so again, in this example, it says plus, but I'm actually shifting backwards, opposite, and this will go down. Okay, and so what that's going to look like when I do it on the graph is I'm going to take each of these points, I'm going to shift left, there's my phase shift, and then down. Left pi over 4, down 1, 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 and that'll give me my cosine graph here. Notice that the graph looks exactly like what we started with up here. I've just shifted it around, and it does keep going. Domain and range are always -infinity to infinity for cosine and sine, not for tangent. We'll look at that in a minute. My range is -2 to 0. It starts here, it stops there. My amplitude is 1. From the midline to a max, or the midline to a min, is 1. My phase shift was left pi over 4. My period was 2 pi, and my vertical shift was down 1. 2 pi for the period, because again, 2 pi divided by 1. All right, so let's take a look at a sine and cosine graph that actually have a compression or stretch. So if I take a look at this, I've really got to take care of this value right here. I have to take this 2 out of the parentheses. Just like in algebra 2, that 2 has to be GCF'd. And remember, when you GCF something, you're actually dividing it. So 2 divided by 2 is 1. There's a 1 right there. But then the pi over 2 is now going to become, the pi is now going to become pi over 2 because I'm taking pi and I'm dividing it by 2 to GCF that out. Okay, so what is that going to do on my graph? Well, I've got to do order of operations at this point because I don't have, translation you can just do at the same time because technically they're just addition and subtraction. You can do them left to right. But in this case, I have a division because remember, I divided this to get pi over 2. So it's going to divide everything in my graph by 2. So I'm going to take this 2 and I'm going to take my sine values, which are 0, max, 0, min, 0, and I'm going to divide them all by 2. 0 divided by 2 doesn't change, but pi over 2 divided by 2 is now pi over 4. Pi divided by 2 is now pi over 2. 3 pi over 2 divided by 2 is now 3 pi over 4. And 2 pi divided by 2 is now pi. So effectively, the graph, as you can see, has been compressed. And that changes the period to be pi. You can see it right there. So the problem is if that were all I had, if I just had sine of 2x, I would be done. But I also have to phase shift this now pi over 2. Remember, this is done. I don't want to look back here anymore. I want to look at this one that I factored out. And so to do that, I'm going to take each of my values and I'm going to shift them. As I said, negatives are actually, since this is the C value, it's actually going to go forward, not backwards. And so I take each of these values that I have and I shift them forward, starting with that 1 at 0, pi over 2. So let's take a look at that. Forward pi over 2, forward pi over 2, forward pi over 2, forward pi over 2, forward pi over 2. And so the graph that we saw earlier, that was here, right? Oops. The graph that we saw earlier that was over here is now going to be here. And that is the root of the graph, but keep in mind that it does go this way and it does keep going this way. So it has a domain of negative infinity to infinity. The range is -1 to 1. The amplitude is still 1. My phase shift is this forward pi over 2. Okay, so my range -1 to 1 inclusive, domain negative infinity to infinity, amplitude's 1. My period is now 2 pi. And the reason that that happens, again, is the algorithm for finding period is 2 pi divided by b, and our b value was 2. So that's how you get the period algebraically. You can also see it very clearly right there. Phase shift is right pi over 2, and the vertical shift, again, you don't see a d here, so there is no vertical shift. All right, let's take a look at a cosine graph that has some compressions and stretches in it. So cosine, remember, max 0, min 0, max. You can see the graph right here. Okay, and now the question is, what will this do? Now, and you might also ask, why would Mr. King start with B if alphabetically maybe we should start with A? This has to do with PEMDAS. So this is a parenthesis, so I'm actually going to do this first. So I take this value and I think to myself, remember, up here, we divided by that value. So you're going to have to divide everything by 1/2. Luckily, the first point you start with, sure is lucky it's 0. It doesn't matter what you divide that by, it's going to be 0. So the x value is not going to change. The y value, again, is going to be controlled by this in a different step. So what ends up happening to the pi over 2 is, remember, we're going to take pi over 2, right, which is this x value right here, and we're going to divide it by 1/2. And when I divide it by 1/2, it's going to reciprocate and become 2 over 1. So this value that's here is now going to be at pi. And the value that's at pi, if I take pi and I divide it by 1/2, right? Remember, there's actually a little 1 right there. So when I reciprocate this, it's 2 over 1. So this value that's at pi is now going to be at 2 pi. And these values are off the chart. They're off my graph paper. 3 pi divided by 2 divided by half, believe it or not, is actually 3. And this right here would just be way off the chart. So we're not really going to pay attention to those in our initial part of our graph. So these values, effectively, you can just erase them if you want to. So we ended up right now with a graph that has done that. So now the question is, what does the 2 do? It changes the amplitude to 2. But it's also, again, from Algebra 2, we would have called that a vertical stretch. A little review on that concept. So I'm going to take these values here, and this value that's at 1 is going to go to -2. It's being stretched and, notice, reflected from Algebra 2. And this value here at -1 is now going to be multiplied by -2, making it go all the way up to 2. So now my graph is much taller and in its origin. And this value here that was at 0, it doesn't move anywhere, because if I multiply this value by, if I multiply this pi 0, if I multiply the output by -2, it doesn't change. So the graph kind of looks like it's diagonal, but remember, this is curvy, you know, mountains and valleys here. So we'll try that one more time. So you have a graph that looks like that. Keep in mind it keeps going forever. Domain, always -infinity to infinity. Range in this case, -2 to 2 inclusive. The range is always inclusive for sine and cosine. So our amplitude is 2. I go 2 from the midline here at 0. I've gone down to or up to, remember, absolute value. The period is 4 pi. Where did I get that from? Remember, the period is 2 pi divided by b, and b is a half. So if I divide 2 pi by a half, I'd have to reciprocate the 2. Remember, there's actually a little 1 right here, and multiply this by 2 over 1, and that's how I get 4 pi. You can also clearly see this is, it's only halfway through at 2 pi, so to go all the way through, if I had more room, would be double that. Phase shift didn't have one, vertical shift didn't have one. You can see that right here. There's no C, there's no D. Tangent's parent function is 0, asymptote, 0, asymptote, 0. And it has half of a tangent here, a full tangent there, and half of a tangent there. And these do keep going, but that would be coterminal. These would be negative. So keep in mind that the parent function of tangent kind of looks almost half-formed in the way that it looks. So you can see that I did that here. 0, asymptote, 0, asymptote, 0. And then, just like with cosine and sine, I'm going to forward shift this pi over 2, and I'm going to shift this up 1. So I take this point, I phase shift it or translate it pi over 2, and then up 1, pi over 2 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 up 1. The asymptotes are kind of interesting, the way you want to think about this. This asymptote is being moved forward pi over 2 and then up, so it doesn't really move, right? Same thing with this one. It's being moved forward pi over 2 and then up, so it just does the pi over 2 and not the upward movement. So I'm left with this dot here, and so that will give us our tangent graph. Our tangent graph will end up looking like this, a little bit more fully oriented once I've shifted it. And there is one over here, right? There's one over here. Those would be coterminal values. These would be the negative values, the negative rotationals. So there's our graph. The range is -infinity to infinity, but the domain always makes kids look like, okay, how do I figure that out? You really have to talk it through. When you look at this graph, there's an asymptote here at 0. So 0 pi, there's an asymptote, right? And then there's also one here at pi, right? 1 pi, and there's another one at 2 pi, and you could understand there'd be one at 3 pi, and there'd be one at -pi. What numbers are -1, 0, 1, 2, 3? A lot of people will say integer. You could call those natural numbers. So it's sort of up to you how you describe this, and this is probably the most routine way, is x such that x is a real number, but x is not equal to integer pi values. Some teachers will say x such that x is a real number where x is n, meaning any pi value where n is an integer. But this is kind of a combination of those two things. It's a little shorter. All right, so let's go over some of the vocabulary. There is no amplitude. So we go back to the vertical dilation concept that amplitude is based on from Algebra 2. You can see how the Algebra 2 review is so important here. So all of a sudden now we don't have an amplitude, we have a vertical dilation. You don't see one, there isn't one right here. My period, remember the period is for tangent is pi over b, right? It's pi over b, which in this case would be pi over 1 here, okay? The phase shift is right pi over 4, you saw that clearly there, and the vertical shift is up 1. All right, let's take a look at our last tangent value, and then I'll show you some calculator things that will help you keep all this straight. So the tangent here, you can see that I've given you one that is a requires a factor out of a GCF. So you're going to take out this 2, make a parentheses, this x, and this is the part we got to be really careful about. When I divide 2 by here, I get 1, but when I divide 2 by pi, I get pi over 2, which is going to shift the graph backwards. But first, because of the order of operations, I have to take care of this right here first. So normal tangent graph, 0, asymptote, 0, asymptote, 0, little half-made thing here, full thing there, half thing there. So you can see that 0, asymptote, 0, asymptote, 0. And now we're going to divide all of the key parent function points by 2. So 0 divided by 2, 0. Pi over 2 divided by 0 is pi over 4. Okay, the next one will be at pi divided by 2 is now at, pi over 2 divided by 2 is now pi over 2. 3 pi over 2 divided by 2 is now 3 pi over 4. And 2 pi divided by 2 is now pi. So you got a lot going on there, but what's happened is everything has shrunk down into here, creating a compression horizontally, right? And so you have your little half tangent there, you have your full graph there, and half of it there. It would keep going, but you can see that this graph is represented here, but what has happened is we have compressed it, and that changes the period to be half of what it would be normally. And that would be it, but I also have to phase shift the graph pi over 2. And this is interesting. Remember earlier in the notes I said that if you phase shift a graph equal to its period, you'll actually get the same graph back. So if I look at this graph right here, when I phase shift this graph back pi over 2, what ends up happening is this graph, this asymptote right here is going to shift over to there, but this asymptote is now going to shift right on top of that asymptote, and that 0 is going to shift right on top of that 0. So by doing this phase shift, I actually phase shift the graph right back onto itself, and that goes back to what I was talking about earlier in the notes. Again, just a quick review of tangent, because it does throw people for a little bit of a loop. The period is pi over b instead of 2 pi over b, and this happens for sine and cosine, but I did this with the tangent one. If you phase shift a trig function equal to its period, the graph appears not to change, and you can see that here in example 6. Okay, and don't forget that we would also have some more asymptotes here, and there'd be another graph going through here, and then another asymptote. It just keeps going. That's really important when we talk about the domain. This keeps going. My range, of course, would be negative infinity to infinity, but my domain is occurring, as you can see, at 1/4, 3/4, 5/4, 7/4, and then it would be 9/4 or negative 1/4 pi. And so what's happening here is the domain is occurring at all real numbers except x cannot equal odd. This says odd in math language, pi over 4. And I think most kids understand if they just say it doesn't happen at odd pi over 4, is they can see it's odd numbers of pi over 4. So the way I got this, again, just to show you that algorithm, is that I took the odd numbers, 1, 3, 5, 7. I called this a 1. The common difference, and this is a review from sequences and series in Algebra 2, is 2. So I plug those in, a1 to 1. I distribute the common difference, I combine like terms, and I get this equation. So in sequences and series, we would write it like that, but in describing domains, we write it more traditionally with the number first, 2n minus 1, as opposed to negative 1 plus 2n. All right, so let's take a look at how we would also, maybe check some of this on our calculator, a little review of some calculator features as well. There's a lot of review when you get to this level in math, and it's important to know where all this stuff comes from. So let's take a look at the first one we looked at, which was sine x minus pi over 2 plus 1 in the calculator. First thing you have to understand is that there is a pi, and so with the pi, I want to make sure my mode is on radian. If this was degrees, if this were minus 90 degrees, I would use degree mode. Very uncommon with graphing, though. We typically graph in radian mode. So you want to make sure it's in radian mode. Then we're going to type it in, okay? And then there's actually a special menu to graph on a TI calculator or a Casio, even on Desmos. If you go to Windows and you go to Zoom, and you go to Trig, Trig is right here. It's choice 7. You can either hit 7 or scroll down to it. But this gives a graph that has all 4 quadrants, which is very disorienting because it makes you think of the unit circle in the wrong way. The unit circle actually starts here at the y-axis. So we're going to go back into our window, and we're going to change this to 0, and we're going to go to 2 pi, so it looks just like the unit circle we do. This tick mark right here is pi over 2, which is very helpful because that's where our parent function 5 values that we have to know go. Okay, remember the 5 values of 0, 0, 0 max, 0 min, 0, they occur at pi over 2 values. My graph paper goes from negative 2.5 to 2.5, so I'm going to put that in. And then when I hit graph, you're going to see a graph that looks exactly like what we drew on our graph paper. Mine's just in black. And obviously the calculator's is a little bit nicer. All right, so let's take a look at the next one. So when we look at the next one, we can look at this graph. This one will have a nice compression on the sine value here. So if I go to y equals and I type in sine of 2x minus pi, the original problem we had, okay, and I graph that, you will see that it looks just like what we have here. Okay, we can even do a cosine one, no problem. We can do a cosine one as well. So when I look at the cosine one, here we go. I have negative 2 cosine of 1/2 x. Okay, I graph that. As you can see, it looks just like what we have, but mine's red and theirs black. So let's take a look at that tangent one. It's a little more interesting, the one that overlapped itself. And we'll type it in both ways so you can see it overlapping on the calculator. If I go here and I type in tangent of, tangent of 2x plus pi, and then I hit enter and I graph the same thing, but I'm actually just going to get rid of that. Remember, if I phase shift the same amount that I have a period, I get the same graph. So tangent of 2x, okay, the first one will be black, the second one will be blue, and you'll see it graph right over top of itself. Black one, blue one. I hope you liked this video. I hope it helped you understand how to graph. I hope it went over some good vocabulary for you. And I hope you have a good time learning how to graph trigonometric functions.